Thank you, Shos. Hi, everyone. I'm Dania Ahmed. I'll be presenting today some work with, in collaboration with Kate Robinson and Alistair Bell from the University of Manchester. So our work is basically about incorporating synthetic turbulence with DDES to simulate the Windsor body flow at yaw angle. So the motivation for this work is basically coming from three areas. The first one is trying to improve the predictive accuracy of the DDES, the delayed detached eddy simulation. So aiming to resolve more boundary layer upstream of the separation, so using the gray area. The second bit is about exploring the aerodynamic impact of large-scale structure in the onset, large-scale turbulence in the onset of the flow, so like that resembling more like real-world environments. And the third motivation point, which is relevant to the second one, is to investigate the sensitivity of the wake to the free stream turbulence. So yeah, certainly, as you can see, the case we're considering here is the Windsor body, so case one, at a small yaw angle of 2.5. So the idea of synthetic eddy method is basically based on the same classical view of turbulence that we got the velocity ui decomposed into mean velocity and then fluctuated bar. So here, let's assume that we got the mean velocity and aij, which is function of Reynolds stresses coming from RAND simulation or even like from experiment. Then what we're doing with u fluctuated j, that's the key thing. So that's basically related to imposing or superimposing number of coherent structures at the inlet. So n number of eddies at the inlet that being superimposed and then projected into aij, which is the turbulence stresses that's coming from RANs, so that we can sort of replicate the turbulence that we see in high fidelity simulations like LES or something. The idea that here we are kind of reducing the CPU time by 3 orders of magnitude. So now we're going to apply this synthetic eddy method closer to the body. So here we see the geometry, the full geometry that we've used, typical to the virtual wind tunnel that extends for 5 body lengths upstream the body and 5 body lengths downstream, with same cross section as the wind tunnel. And then for the case where we have the synthetic turbulence, we are placing the synthetic turbulence just one body length out upstream the body. So we're kind of reducing the computational area domain. Now, the details of the mesh that we've used here is similar to G2 for the case that we don't have the SEM. It's exactly G2 mesh that was provided. So it's around 32 million cells. And then when we apply the SEM, we truncate the geometry, but then we kind of had higher mesh because we needed to refine the mesh slightly in the upstream box. So solver reviews this finite volume based, which is open form, and then all the discretization schemes were second order. For the turbulence modeling, we're using DDES with K omega SST, and that was parallelized over 20 nodes using Archer 2. And then the simulation was run for around 62 convective time units. So now, without the SEM, the synthetic turbulence, the simulation here, if we convert just the results of the DDES compared to the experiment, we can see on the left that the experimental, like the top view at mid-height of the mean streamwise velocity compared to the DDES on the right. So we can see a good match to some extent. And similarly on the base pressure, the CD, the time average drag for our DDES results kind of less by 10% compared to the experiment. We'll accept that for now, and we'll see the results of the SEM now. So for the SEM setting, synthetic eddy method, we have 3 parameters to think about. First of all, the inlet turbulence, which when we mentioned that, we're thinking about the size of the eddy that we're imposing at the inlet and the Reynolds stresses. Second thing is the distance between the inlet and the body, that we already assume that's only one body length. And the third thing is the size of SEM. So in our case, we've reduced it. We didn't impose the SEM over the whole cross-section of the wind tunnel, but only like a smaller section, so as we can reduce the computational power needed. So what we were doing at the very beginning is to study sensitivity of SEM to inlet eddy size. With that, we end up with 4 cases. The first case is the case without SEM. Second case, we've imposed eddies at the inlet. So sigma is the size of the eddy. We impose the eddies at the inlet with a size of 0.01. So that's 20% of the height of the ground boundary layer. And then the second case, we've increased the length scale up to 50% of the height of the boundary layer. The third case is more of a realistic case. So here the eddy length scale is the same as approximately the body height. So that's almost 5 times the height of the ground boundary layer. For all the cases, Reynolds stresses at the inlet are coming from RAN's simulation for the same case, for the same mesh, sorry. Now, if we look here, we can see the geometry that we've used. The SEM inlet that was placed the body length upstream, and then its cross-section height is around 1.7 times the body height, and the width is 2 times the body width. Now, a good thing to look at before running the simulation is if we are resolving the turbulence in this upstream box or not. So here we see a comparison between the eddy intensity for different cases and also like the number of cells per eddy, roughly, for each case. So when we look at sigma equal 0.01, the smallest turbulence intensity scale, we are using 19 cells per eddy. That's the volume ratio. And then that increases up to the third case of sigma equal 0.3, and that's all resolved with more than 500,000 cells. So then that's why we got larger mesh in this case, although we have a truncated geometry. But then we extend the same mesh resolution around the body in addition to the prism layers, and then also in the near wake and far wake regions. Now, if we look at the results of the upstream turbulence, it started with the smallest length scale, and here we look at the isovolumes of Q, that's between 200 and 500, and we can see that the turbulence coming from the upstream, colored by vorticity magnitude, and then to some extent kind of dying before reaching the wake, as we'll see later. But this is just to give an idea of the length scale of coherent structure that we are imposing. Now, if we increase that size and look at the same quantity, the same range, we can see that here we have larger coherent structures upstream the body. For this case, which is, we think we have some numerical issues, as you can see the gradients on the top there, but here we just give an idea of the size of coherent structures upstream the body, and that will be more relevant to investigating realistic cases. It's like if you have a bluff body in front of the Windsor body, or more like a wake of an obstacle. So we didn't take the results of this case into consideration at the moment, but we are still investigating it. Now, if we look at a top plane to compare the vorticity in the presence and absence of SEM in the upstream, on the right we can see this is the DDES results without SEM, and on the left there are the 2 cases with different turbulence length scale at the inlet, and we can see clearly the difference in terms of vorticity. Same thing on the side, and that clearly shows the kind of development of the turbulence around the body, and that the mesh and DDES both are capturing that very well. Now, if we look at the turbulence intensity halfway upstream the body, we can see that we are generating a turbulent intensity between 0 and 3 for the smallest length scale, between 0 and 5 for the mid-length scale, and for the highest between 0 and 14. And then the area average area average turbulent intensity for each case is going between 0.5 to 4. So, and yeah, as expected, we got high length scale around the ground boundary layer and then less everywhere else. So, last thing to look at in terms of the upstream turbulence is that this turbulence imposed upstream doesn't cause any sort of flow separation for the ground boundary layer. The only thing that we've noticed that there is a slight increase of 1% in the second case where we have a sigma equal to 0.03, slight increase of the thickness of the boundary layer. Then if we look at the turbulent kinetic energy, we can see clearly that in the case where we have sigma of 0.01 in the bottom left, we can see that, yeah, there is turbulence kind of coming from the inlet, but it's dying before reaching the wake. While this is not the case for sigma equal to 0.03, we can see that there is turbulent kinetic energy being developed and some interaction with the wake downstream. And finally, if we do a quick comparison for the wake and drag in the presence and absence of SEM, for the base pressure, for the base CP, we can see that there is sort of, in terms of distribution, not much of differences between all cases, and the presence of SEM decreases the base pressure, and max reduction of like kind of 2.7% for the mid-length scale. And then that for sure would increase the drag. So the time history of drag showed that for all cases we got, time average drag showed for all cases we got an increase, but that's less than 1%. While if we look at the probability density function for the drag for each case, we can see that the mid-length scale increased the peak of the probability density function by 4%. Now, if we look at the frequency spectrum of CD without the SEM, we can see different dynamics, similar, matching what's reported in the literature. So we can see low frequency dynamics that's normally relevant to reflection and symmetry breaking, and in the absence of Yao, that would be bimodality. And then we see low frequency dynamics also related to what we call bubble breathing. So that's a streamwise motion of the recirculation region. And also vortex shedding around Struhan number of 0.16, and finally high frequency dynamics of associated with Struhan number larger than 1. Now, when we apply the SEM at very low frequency, at very low length scale, this would have the highest frequency, as we can see with this orange dotted line, dashed line, sorry. So the main change here is that we can see more noise at high frequency, the high frequency spectrum. Which is expected, but nothing much changed in terms of the low frequency dynamics. Similarly, when we increase the length scale to 0.03, we can see that we have less noise, so still have some noise added compared to the no SEM, but less compared to sigma 0.01. And upstream turbulence still like spectrum remains kind of more or less the same. In the last case where we have very low frequency of almost 1, we have almost no change in the high frequency and a bit of change in the low frequency. So yeah, and then we looked at the low frequency dynamics, which is related to reflection and symmetry breaking or bimodality, to check if we have wake switching or not. And here we are using the base pressure gradient. So we are calculating CP, the difference between the pressure along A and B, difference between CP along A and B, that's divided by normalized distance between the two, which is 0.9 here. And the time history for that quantity showed the probability density function stayed on one location. Sorry. That means the weight kind of remains asymmetric and skewed toward the windward side. And that what we can see here, so this is the largest coherent structure in the near wake region. For the case where we have SEM of sigma equal to 0.03. So we're not affecting the low frequency dynamics as we can see here. Now finally, if you compare the mean weight, the mean stream velocity of a plane, of a vertical plane. On the top left, we can see the mean streamwise velocity without the SEM. Then the green line represents the length of the recirculation region. And then what we can see here is like there is a slight change for sigma 0.01, but then for 0.03, that will be more like kind of more seen that there is a bit of reduction of the length of the recirculation region. That's always associated with an increased drag. Then yeah, for the cross section downstream, just downstream the base, no change could be seen. In the presence, I mean, applying SEM doesn't change much the cross section of the recirculation region. And finally, if we look at some answers for if the SEM would improve the accuracy of DDES or not. Here we are looking at the mean stream velocity along lines in the mid-plane. So we can see that DDES is kind of along the line over predicting the mean streamwise velocity, especially in the jet that's coming from the underbody flow compared to the experiment. And now applying the SEM doesn't change that much. And if we look at the turbulent kinetic energy.
Sorry, can I ask you to conclude?
Yeah, sure. Sure. This is actually my last slide before the conclusion. But yeah, like turbulent kinetic energy increased a bit in the presence of SEM as expected. And to conclude, this is an ongoing work. So we have already successfully applied the SEM to investigate the flow past the Windsor body. And we've generated turbulence intensity between 1 to 4%, which is still less than the realistic cases, but that's to be investigated later. And an average free stream turbulence intensity of 1%. We've seen it to increase the peak of BDF of drag of CD by 5%. So again, lastly, SEM doesn't improve the DDES so far, and we're still investigating. So thank you very much.